Hello everyone. Welcome to the first live student talk that we, the Math Club, are organizing. Today we have Anand from the fourth year, BSMS. So without further ado, Anand, please take over.
Thanks a lot. So yeah, I'm glad to be giving a student talk because like when I was the first year, the math club used to organize a bunch of these, and I think that sort of pushed me towards math. So yeah, I'm glad to be giving this sort of talk, and I hope there are more to come. If some of you in the audience want to give talks, then feel free to contact the math club. Right. So today I'll be talking about this connection between two seemingly unrelated things. On one hand, we have this game called Hex. It's a board game very similar to tic tac toe, as we'll see soon. Uh, And on the other hand, we have this theorem concerning disks and maps and fixed points. It's a very fundamental result in algebraic topology called Brouwer's fixed point theorem. So this talk will be about the connection between the two. And let me emphasize that I am giving this talk with first years in mind. You don't need to know anything about algebraic topology whatsoever to understand this talk. And if at any point you feel lost, feel free to interrupt me and uh, ask questions. So this talk is going to be a very short one. Hopefully we'll be done by 6. Roughly, here's what I plan to cover. First, I'll introduce you to the game of Hex. Then I talk about the second thing, second important character in the story, which is Brouwer's fixed point theorem. And as I mentioned a while ago, we'll prove that the two are equivalent. And we do this in 2 steps. First, proving that the Hex theorem, first proving that the Brouwer's fixed point theorem follows from Hex theorem, and again, vice versa. And yeah, that's the main content of this talk. I won't be presenting proofs of these two theorems themselves. Those are fairly standard and can be found in a lot of places. The main focus is on the equivalence between these two theorems. Very well known and seemingly different theorems. Right. So yeah, this is essentially what I said. So on the hand, we have this game called Hex. It's a very simple combinatorial game. And on the other hand, we have this theorem concerning disks and maps and so on. And yeah, this is so we'll start with the first character in the story, the game of Hex. Games are probably more fun to start with anyway. So Hex was invented around 100 years ago. It was first invented by this person called Piet Hein. I'm not sure if I'm pronouncing this right. So he was a Danish engineer and poet. And later on, this game was independently invented by John Nash, like the John Nash, the very famous one. And so before I get into the theorem, I'll first state the rules and explain roughly how the game goes. So you have this grid over here, an n by n grid filled with hexagons. That's why the game is called Hex. And over here on the top, the hexagons are lined with red, and likewise at the bottom. And on the left, you have a bunch of blue hexagons on the border, or blue borders. And on the right, you have a bunch of blue borders as well. So how this goes is that players take turns in placing tiles of their color. So there's a blue player, there's a red player, and the blue player and red player alternate in placing tiles on empty squares. And this goes on forever until the entire board is filled up. And a person wins if they manage to get a continuous thing across the entire board. So for example, blue player might play this first, then the red player goes, and this goes on forever until the entire board is filled up. And the blue player wins if there's some sort of a continuous path like this, passing through hexagons, connecting the two ends of the board. And it's not too hard to see that if the blue player wins, the red player cannot win, and vice versa. So that's how this game works. And yeah, these are the rules if you want to have a look at them. And to better understand this, let's play this out live. And this link is supposed to work, but it's not. Give me a second. I'll quickly sum up this link. Just a minute. Here it is. Okay. So I'll post the link in the chat. So hopefully you should see something like this. Uh, a bunch of hex boards. So this is co-create. We use this in Math Mamsa meetings. So you can give yourself a name up here in the top right corner. You can select a color at the bottom. So select blue if you want to play as a blue player. Select red if you want to play as a red player, and battle it out. I've explained the rules, but you can clarify if you want. And you can just hover around the board waiting for someone to join. And once you have another player with you, like you can, yeah, you can start. So I'm blue over here, and there's a red person over there. So I'll start off with blue. So I've marked my square, and yeah, go ahead, somebody. Yeah, sure. Also, wait, let me know if there aren't enough boards. Like there are, I've scattered a bunch of boards, like I think 20 or so, like all over the screen. So ideally there should be enough, but let me know if there aren't. Okay, things don't look good for me. Oh no. Okay, yeah, I think I lose because there's a continuous red path all the way. Yeah, so I've lost. I mean, we could keep playing. The game ideally goes on until we're all done, but yeah, I mean, it's pretty clear who the winner is at this point. There's no way for me to undo that red streak, and yeah, there's no way for me to get across. So, wait, somebody erased a board. I will have a look. Uh, so like yeah, there are a bunch of boards scattered over. So you can take your pick. Also, are the rules clear to everyone?
Like so, we have to put markers on there turn by turn, and the first one to make a clear connected path wins. So, are there any other rules? Like I was
Yeah.
disconnected.
Yeah, so the blue player has to connect the blue paths and the red player has to connect the red paths. So yeah, let me find a blank board. Yeah, so if I'm playing blue, then my objective is to connect these two ends. If I connect these two ends, then it doesn't count. It has to be these two. So likewise, if I'm the red player, I need to connect these two ends, not these two. So yeah, those are the only rules.
All right.
Also, yeah, this is a good idea. Like you can use text to chat. Okay, I see that a lot of people have almost finished. I guess I'll wait for a minute or two and then go back. Okay. Maybe I'll go back for now and uh, yeah, you can keep playing. The link will be open. Um, so yeah, so I guess at least a few of you have completed the game. So can you message in the chat whether your game ended in a draw or there was at least one winner? Like maybe plus if there was a winner and minus if there was a draw. So my game ended with a plus. So yeah. Okay, so I see a few pluses, but I don't see any minuses. All right, so there are a bunch of pluses, and this is no coincidence. Turns out this is a theorem. So John Nash proved this, and the theorem is that the game of hex always has a winner. Actually, he didn't prove exactly this. He proved something slightly stronger. So if he proved that if you take a hex board and color it randomly, like so when we're playing a normal game of hex, there are roughly equal number of blues and reds. But he said if you take a hex board and color it randomly, uh, then you're guaranteed to find either a path of blues connecting the left and right, or a path of reds connecting the top and bottom. So it's a remarkable result, and this sort of explains why there are no minuses in the chat. Like nobody faced a draw. So this is very nice. If you contrast to tic-tac-toe, like tic-tac-toe is frustrating because in a lot of cases it ends with a draw, and it's kind of a boring game. So next time you're bored and want to play a board game, play Hex. Uh, right. So let me try to give some intuition for the Hex theorem. So let's try to think of the blue tiles as representing water, and the red tiles is representing land. Uh, so can someone put these together to give some intuitive explanation of why we would expect only why would we always expect a blue path connecting the two ends or a red path connecting the two ends? I'm not expecting a proof, like just an intuitive explanation based on this analogy with water and land works.
Uh, so this sort of implies that either one has to be contiguous, right? From one end to the other.
Right. Could you elaborate?
So uh, if you color all the tiles randomly,
Right.
so the only way, uh, say, blue cannot reach the red side is if red stops it. And the only way red can stop it is by completing its own path, and vice versa.
Exactly. Yeah. So red is sort of like building a dam to obstruct the flow of water. So if the dam is not complete, then water will find a way through and make its way to the other side. So the only way to contain the water and preventing it from reaching the other side is to build a barrier spanning across the other end. So I hope that intuition is clear to everyone. And yeah, that's an intuitive explanation for why we would expect such a thing to hold. And yeah, that's the remarkable thing about Hex. You can never have a draw, unlike a lot of other board games. And in fact, we can say something stronger. So we can say that the first so not only does the game never end in a draw, one of the players has a winning strategy. That means one of the players can always force a win, and that player has to be the first player. So if you people were there for last week's Mathnompa meeting, this might sound familiar. And uh, the proof is also quite similar to some of the stuff that we discussed. So I won't discuss this right away because I'm already planning to discuss two proofs. But if there's time towards the end and some of you want to hang around, we can try to work through the proof of this together. Right. So does anyone have any questions regarding this game so far, or like should I move on? I guess we'll move on. So we come to Brouwer's fixed-point theorem, which is the other part of the story. So before stating the theorem, I'll try to motivate it with a few examples. So let's say I have a cup of coffee, and which has a layer of cream on top. Now let's say I stir the cream. Remember, I'm not stirring the coffee. I'm just stirring the layer of cream on top. And this is a continuous motion that I'm doing. I'm sort of basically moving things around, mixing things up only on the surface. And let's say I take a picture initially before mixing things, and I take a picture much later after I've mixed things up and made it chaotic. So Raoult's fixed point theorem says that no matter how vigorously I mix it and no matter how chaotic it is, there will always be like one tiny bit of foam, one tiny bit of cream uh, that ends up exactly where it started. Like, so if you compare the two pictures and you somehow label each bit of cream, you'll find that one bit of cream is exactly where it started, no matter how vigorously I shake it. So yeah, that's a kind of a surprising result. It's more like a consequence of Brouwer's fixed-point theorem. And here's another example. So let's say I have a map of a place. So this is a map of the IISER campus. And let's say you print this out and like fling it on the floor somewhere. So I'm currently over here somewhere. I'm in the guest house quarantining. So yeah, let's say I print this out and I fling it somewhere on my floor. So Brouwer's fixed-point theorem tells me that there's going to be one point on the map that's a you are here point. So in other words, it lies exactly above the point that corresponds to in the map. And this is always the case. As long as I throw the map somewhere on campus, there will always be one point that is directly above the point that it represents. So these are two very cool consequences of Brouwer's fixed-point theorem. And I'll go ahead and state what it is. So if you want the rough intuitive version, this is what it is. So Brouwer's fixed-point theorem says that if you have a disk and a continuous map from the disk to itself, then this map always has a fixed point. A fixed point is a point that does not change after applying the map. If you want to state things a bit more formally, you can state it this way. So let's say B is the unit disk, the closed unit disk. So basically the circle in the complex plane, you can think of something like that. And you have a function going from this disk to itself. And an important criterion is that it has to be continuous. So any function won't work. It has to be continuous. And what this says is that you can always find a point in the disk such that it maps to itself. In other words, if f is the function, there's a point x such that f of x is the same as x. So, so if as you follow along the proofs, like you'll sort of see that this is not exactly what we'll be proving. We'll be proving something that's logically equivalent but different. And so this is more like a constructive version. So when we say that there exists a fixed point, we're sort of cheating a bit because we're not actually giving a fixed point. So ideally, if you're doing things constructively, you want to actually give a fixed point when you say that there exists one. But what we'll do is we'll just indirectly show that there must exist a fixed point without giving any indication whatsoever of where it exists in the disk. So in other words, we're proving something that resembles this statement. So we're essentially proving that if f is a function from the disk to itself, then it cannot displace every point. So in other words, it's not true that for all x, f of x is not equal to x. That's actually what we're proving, but these two are logically equivalent classically. So the reason I bring up constructivism is that Brouwer was actually a constructivist. So Brouwer had this belief that uh, mathematics should be constructive and based on intuition. So in other words, when you actually make a claim, like there exists something, you actually need to show it. You need to show an example of it. And you can't just get away with making some indirect thing by canceling two negations or the kind of stuff that we do in math. So some people dismiss Brouwer and think his ideas are crazy, but when you come up with a constructive algorithm, you're actually coming up with a program. If you say that exists a point and you have a constructive proof of it, then you actually are giving a program which you can run and actually get the fixed point. So that's what a constructive proof would look like. And all these theorem provers like Lean and so on are based on this constructive logic, which exploits this connection between proofs and programs and so on. And like so constructivism isn't nonsense, and like it's actually a very nice thing to think about. But anyway, back to the talk. So in Brouwer's fixed point theorem, I made it sound very specific because I was talking about this particular closed unit disk in the complex plane. But it actually isn't as rigid as it seems, because I'll show that if we have a space that is sufficiently disk-like, then the Brouwer's fixed point theorem applies to that as well. So I'll sort of formalize what it means to be sufficiently disk-like before giving some intuition. Yeah, so let's say the disk is made of clay. So you can move this clay around, you can mold it, you can stretch it, you can flatten it, and so on. But the only thing you're not allowed to do is tear it. So anything that can be obtained from a circle, from a clay circle, by stretching, squishing, deforming continuously is considered similar to a disk. So a square, for example, is similar to a disk. So is a hexagon, and so are a lot of other shapes. But anything that is obtained by like tearing or any other such violent motion is not similar to a disk. So in other words, we said two things are similar. If there's a continuous way to go from B to X, B is the closed unit disk that we're considering, and X is some random space. So if there's a continuous way to go from B to X, and moreover, there's a continuous way to go back from X to B. So the square is such an example of something that's sufficiently disk-like, and so is a hexagon. And here is sort of a sketch of a proof for why Brouwer's fixed point theorem holds for sufficiently disk-like objects and not just disks. So let's say we have this space X, which is disk-like, and we have a continuous map from X to itself, right? So Brouwer's fixed point theorem is, as of now, is something concerning B, which is the closed unit disk. So we use F to construct a map from B to itself in the following way. So we know that X is disk-like, so we can turn B into X, and then we can apply F, the function that we have, and then what we get lies in X. And since X is also disk-like, we can turn back into B. And if you're fond of notation, this is what it looks like. We're defining F tilde to be first apply H, then apply F, then apply H inverse. So That's what this map looks like. And by Brouwer's fixed point theorem, we know that this thing has a fixed point. In other words, there's some x such that f of x, I mean f tilde x is x. And if we expand things out, f tilde x is just this. So we expand things out, and we're saying that there's some x satisfying this relation. But then h inverse, so h is invertible. So this is the same as saying that f of h of x is the same as h of x. But if you go back and look at the definition of fixed point, this is essentially saying that h of x is a fixed point of f. So the long story short is that Brouwer's fixed point theorem is not specific to just closed unit disks in the complex plane. It's much more general and applies to anything sufficiently disk-like. And we'll use this fact in later proofs. Right. So to make sure that we've understood Brouwer's fixed point theorem, let's look at a few examples. So first, let's look at the identity map. Can you name a fixed point?
Any point?
Every point is a fixed point.
Yep. So any point is a fixed point. If I start off with this point over here, it'll end up here, and it's a fixed point. Yeah. All right. So what about a rotation? To make it more concrete, what about a rotation by like 90 degrees to the right? So this point will end up here, so it's not a fixed point. But can you find a fixed point?
Center.
The center.
The center.
Yeah. So the center. So by Brouwer's fixed point, so Brouwer's fixed point theorem just says that there exists a fixed point, and we found one. So the center is a fixed point. Right. What about a flip? So you start off with something over here, and it turns into this. So does this have any fixed points?
Still
The point over which we flip.
diameter.
The diameter. I think that's what all of you said. Yeah. So you're right. Yeah, the diameter. Yeah. So anything on this diameter is a fixed point. What about a constant map? That means anything over here maps to a single point over here. Does this have any fixed points?
The center.
No, that's not.
The point to which it mapped.
Yeah, the point to which it maps. Yeah, you're right. If everything maps to, let's say, this thing. Or wait, how do you erase this thing? Yeah, you're right. If everything maps to this thing, then in particular, this thing maps to this thing. Or maybe I'll replace this thing with x, and I'll say this again. Let's say you have a point x over here, to which every point in this disk maps. All right, so in particular, x maps to x. And so that's why x is a fixed point of f. Right. So what about this example? Something that's almost constant. So everything except, let's say, 0. So this, let's say this is 0. Everything except 0 maps to 0. And 0 wanders off somewhere over here.
This
Does the map make sense?
This is a discontinuous map, so the theorem does not apply.
Exactly. Yeah, exactly. So yeah, this does not have any fixed points, but that does not violate Brouwer's fixed point theorem because it's not even continuous. So Brouwer's fixed point theorem requires continuity, and this is not continuous. Continuity basically means that nearby points map to nearby points, and everything near 0 maps to 0, but 0 wanders off somewhere. And so, yeah, this is not continuous, and yeah, that's why it doesn't have any fixed points. Does anyone have any questions?
So in this case, a map is defined as a function of a circle to all the points in another circle.
Yeah, it's a set theoretic map, and we're imposing continuity on that.
Yes. Okay.
Yeah. All right. So if there are no questions, I'll move on. So this is the first part of the proof. And yeah, so I'll go ahead now. Yeah. All right. So when we spoke about the hex board, we looked at something kind of like this, a bunch of hexagons, and they're all connected, and this is the blue end, this is the red end, these two are the blue ends, these two are the red ends, and yeah, this is the situation that we looked at. But we can sort of simplify this a bit. And instead of looking at each hexagon as a hexagon, we look at it as just a point. For simplicity, just consider its center. Right? And then we can also draw lines between two adjacent hexagons. So these two hexagons share an edge. That's why there's a line between them. Likewise with these two hexagons. And yeah, the pattern continues over here. So essentially, we're sort of modifying the setup a bit, and this will be helpful in the proof. So instead of looking at this entire hexagonal grid, we just look at this mesh sort of thing of triangles. All right. So just to make sure everyone's on the same page, this is what we're doing. So we want to prove the Hex theorem, and we're assuming Brouwer's 6-point theorem. So Brouwer's 6-point theorem is this map about functions and disks and so on. And Hex theorem is something about the game of Hex and the Hex board and so on. So first of all, to even bring in these tools of algebraic topology, to bring in the tools of Brouwer's 6-point theorem, first of all, we need a map, and second, we need a disk, and we have neither. So let's try to bring in a map first, and then we'll try to bring in a disk, and then we'll try to apply Brouwer's 6-point theorem to prove the Hex theorem. So, right, so here's our first step in the proof. So we're color coding each of these hexagons. Hold on. Yeah, these. Yeah, we're color coding each of these hexagons according to this rule. So let's say we're looking at a colored grid, and we're we say a tile is in this set B plus if it's a blue tile, and moreover it's reachable from the left. That means it has a path starting at the left of the hex board and continuing all the way till this point. And anything that's not in B plus is in B minus. Likewise, we say a red tile is in R plus if there's a path from the bottom of the board to that red tile. And we say if it's R minus if this is not the case. So let's try to look at a concrete example. So let's say this is blue, this is blue, blue, blue. I'm coloring randomly at this point. Blue and red, red. All right. So I've colored the entire board. What do you say this tile is in? What class do you say this tile is in? Like, is this a B plus or a B minus?
B plus.
So I'll go back to yeah, it's a B plus because of the coloring is still there. So I'll just write a plus over here because it's a B plus because there's a way to reach it from the left end of the board. What about this tile?
B minus.
That's a B minus.
Yeah,
B minus.
a B minus, and these two are also B plus. Let's look at some red tiles now. So what about this red tile?
R plus.
Yeah, this is R plus, and so is this for simple reasons. This is also an R plus. What about this?
R plus.
Are you sure? Oh yeah,
Yeah, you have a part.
yeah. What about this?
No, that's an R minus.
Yeah, you're right. This is R plus. This is R plus. And yeah, I think you get the idea now. Yeah, I think you get the idea. So we are looking at a filled board, and we color code it according to this scheme that we just saw. So either B plus, B minus, or R plus and R minus, right? And now we're at a stage where we can define a function. So this function is just operating on these points. So remember, we made the simplification of going from hexagon to a point. So instead of this hexagon, we're now dealing with only this point that represents the hexagon. So yeah, this function over here. So let's define some notation first. So there are two directions over here, right? You can think of this as a square grid. So there's a horizontal direction and there's the vertical direction. Wait, this grid is a bit messy. Let me clean things up. Yeah, so there's a horizontal direction and there's the vertical direction. So let's, and any point over here can be described uniquely as like two positive integers, like one describing its horizontal position and one describing its vertical position. In other words, these two vectors sort of span the entire grid, like this entire set of points. So let's call this unit vector EH and this one EV. EV, sorry, yeah, excuse my handwriting. Yeah, so this is EH and this is EV. And these are basically the unit horizontal and unit vertical vectors. Right. So we define this map, F. So it's a piecewise map. If X is in B plus, then you're shifting the point to the right. So in other words, you're adding EH. You're shifting it one step to the right. If it's in B minus, which means that it's not reachable from the left, you're shifting it to the left. And again, if it's in R plus, which means that there's a path from the bottom, you're shifting it to the top. You're shifting it one unit to the top, and otherwise you're shifting it downwards. So is this all? Does this always make sense? Can you take a random board and can you do this? Can you apply this map and get something well defined? Okay, let me try to make that more concrete. So can you get something that goes out of bounds? Like can you push a tile? Can you push a tile off the edge? Like, do you think that's a possibility?
Yes, if one of the red tiles is at the top, like it is already connected, then
If one of the
apply
red
this
tiles,
one.
exactly. If one of the red tiles is at the top, then this function moves it further to the top, and that's impossible because there's nothing above it. So it's not well defined if there's a path connecting the top and the bottom, a red path connecting the top and bottom. What about the, yeah, so like can you generalize this? Like can you say something similar about blue?
It's basically if the blue tile is at the rightmost type. Like if there are any parts connecting there, then it gets pushed off the edge.
Exactly, yeah. So this does not make sense for boards in which the Hex theorem holds. Like, so remember, we haven't proved the Hex theorem yet. So if there's a path connecting the left and right, or if there's a path connecting the top and bottom, then this function does not make sense. It makes sense only on boards where there's neither a path connecting the left and right, nor a path connecting the top and bottom. So this is the kind of board that we are working with, and we want to prove that this sort of board does not exist. So in other words, this function will eventually lead to a contradiction. In other words, this sort of board cannot exist, which is what we'll get to know. So we're only half the way there. Like we've defined a function, but we want to get a continuous function between a disk-like thing to a disk-like thing, and we're not there yet. So for that we'll need to know this fact about triangles. So let's say we have a triangle. This is a triangle, and we have a point P in the triangle. Then it turns out that you can uniquely describe P by these three numbers, lambda1, lambda2, and lambda3, which sum up to 1. Intuitively, you can think of it this way, like you have this triangle, you place a bunch of weights on each of the vertices, and each weight determines how much influence that vertex exerts on the point. This thing is small, so P is not influenced very much by this vertex, but this thing is quite large, so this point is influenced quite a bit by this vertex, and likewise by this vertex. And you have the constraint that these three numbers add up to 1. So this point P is sort of like the center of mass of these three masses, like if you want to think of it intuitively. So that's sort of how it is. And yeah, this will take as a given, but you can try proving it if you want. Hopefully it's intuitive enough at the moment. Like at least this seems not unreasonable. And with this fact in mind, we go back to our grid over here. So we've defined our function on each of these points. And we want to somehow extend it to an entire disk-like object. So we said a square is disk-like. So we'll extend it to this entire square-like thing, or like more precisely a rhombus. So this thing is made of a bunch of triangles, right? So it's made of a bunch of triangles, and the idea is to fill in the interior somehow. So we've seen that any point P can be written as lambda one, like this. Basically, we have this fact about triangles. So let's say we have an arbitrary point P, then P lies in a unique triangle, right? So, and let's say the vertices of this unique triangle are V1, V2, and V3. And V1, V2, and V3 are vertices. So that means F is defined on them. And we extend F to this point P in the interior as follows. So we have these numbers lambda 1, lambda 2, and lambda 3. We use them as weights to sort of adjust the pull of this function. So F of V1 and F of V2 are, basically F shifts a point either in the upward or upward or rightward direction. And this is sort of like fine-tuning those pushes by these weights to obtain something intermediate. And this is also continuous because usually, as a rule of thumb, anything arising from some physical scenario is continuous. And this is sort of a physical scenario because you have these weights exerting influence and all that. So yeah, so this F, which started out as a function on the vertices, now extends to a function on this entire square-like thing over here. And now we have a function in a square. We sort of argued that it's continuous, and it maps to the square itself, provided there's no path connecting the two ends. And so, what can you say now? We're in a position to apply some of the stuff we spoke about. Does anyone want to take a guess?
Like we are shifting one point to the other, so essentially we are creating a map, I suppose.
Yep.
So there has to be at least one point in this mapping which will not change after applying this.
Yeah, great. Yeah, you're right. So essentially, you've applied Brouwer's fixed-point theorem to this. So yeah, we're assuming Brouwer's fixed-point theorem, and we're trying to prove the Hex theorem. So yeah, we've assumed the Brouwer's fixed-point theorem, and a fixed point. And let's go back for a minute and try to see what it means to be a fixed point. So if f of p is equal to p, so f is sort of exerting all these tugs in these various directions, right? So it's a weighted sum of all the tugs of all the vertices. And this is a fixed point. So that means the vector sum of all these tugs must be 0. And so I claim that's impossible. Can you say why? Or maybe I'll say a bit more before leaving it to you. So it cancels out in all directions. And lambda 1 plus lambda 2 plus lambda 3 is 1. So at least one of these is non-zero. One of these tugs is non-zero. So let's say that is pulled in like the upward direction. Then there must be a net downward force from the other two things. And going back to the map, when can you have a downward tug? Going back, yeah. When can you have a downward tug? Like we're saying there's an upward tug, so it must be coming from something in R plus. So when can you have a downward tug?
We can have a downward tug if it is not if it is in R minus, but a thing cannot be simultaneously in R plus and R minus.
You're very close. So that means one vertex is in R plus, we are assuming, and we're saying that one other vertex is in R minus of the same triangle. So that means we have two adjacent vertices in R plus and R minus. So is that possible? Like, can we have two adjacent vertices? I'll go back to the definitions of R plus and R minus. Can we have two adjacent vertices, basically two vertices of the same triangle, one in R plus, one in R plus, and one in R minus?
No. If one vertex is in R plus, the adjacent all vertices must be in R plus.
Exactly. Yeah. Everything else. Yeah. Because if this is connected, then you can just extend that connection one bit more. So you're right. That's impossible. And I just chose the upward direction, and but you can see easily that that's without loss of generality. Like you can make the exact same argument for the rightward tug. So in either case, you can't have a fixed point of this map. So that's a contradiction. And what was our assumption? So if you go back here, our assumption was in defining this function f. So f is defined only if uh, the conditions for Hex theorem are not, only if Hex theorem is not already true on this board. So that means you can't have an instance where Hex theorem is not true. In other words, Hex theorem is always true. So that proves Hex theorem from Brouwer's 6-point theorem. And now we'll try to go the other way. Right. So Brouwer's 6-point theorem, as we saw earlier, is a theorem concerning circles, disks, maps, fixed points, and so on. And we've seen that it's not strictly necessary to have these circles all the time. Like it's fine to pick a square or a hexagon as long as it's sufficiently circle-like. So because I know that it's convenient going on, I've chosen to prove it for a square without loss of generality. So let's assume we have a square and we have a map f going from the square to itself. Yeah. So again, our trick is going to be to color code the square somehow. So we take the square and we look at some random point p, and look at f of p, which is again a point on the square, right? Like f is mapping from the square to itself. So let me draw things here. So let's say we have the square. We have a point. This is its image, the blue thing. Okay, it was supposed to be blue, but that's fine. Right. All right. So H plus, basically all those points where the image is to the right of the point, in the general rightward direction. So it can be a little up, it can be a little down. As long as it's in the general rightward direction, we put it in H plus. And likewise, H minus is where the image lands slightly to the left of the point. Again, like general leftward direction. It doesn't have to be exactly in the same line. Like it can be like a little to the left and right, or I mean, little to the left and up, or left and down, and so on. As long as it's in the general leftward direction. And completely analogously, we define V plus and V minus. V plus consists of all those points that lie above their starting point. So this would be in V plus, for instance, because its image is slightly above itself. It's in the general upward direction. And likewise, V minus is for the point that go below. So here's a question for you. Can a point be in both V plus and H plus at the same time?
Yes.
Yeah.
Yeah, diagonally
Yeah.
towards.
Yeah, the one I've drawn is in both V plus and H plus.
It's sort of like defining quadrants, right?
Yeah, kind of, yeah. And yeah, H plus and H minus together is impossible. Like I guess it's obvious to everyone now. V plus and V minus. You can't have a point that's both in V plus and V minus. Sorry, somebody had a question.
So if the point is, for instance, if you take any points and draw the lines parallel to the sides of the square, if the transform point lies on that line, so it's neither defined as H plus or H minus, right? Or V plus or V minus.
Could you repeat?
Like if it lies along the line parallel to the sides of the square, then it falls in neither H plus nor H minus, or V plus or V minus, depending on.
Yeah. Yeah,
So
good point.
it's
Yeah, good
inequality.
point. So yeah, if we have something, if the image was this instead, like so if the image was somewhere over here, like something like this instead, then it's in neither H plus. Wait, it's in neither V plus nor V minus, but it's in H plus. So it's in one of these things. So can you tell me when something is in none of these regions?
If it maps to itself.
Yeah.
Exactly, if it's a fixed point. So yeah, we've cleverly constructed these regions such that the only thing that's not captured by at least one of these regions is a fixed point. Right. And also we've said the function is continuous. So let's say a point is in H plus, which means that its image is slightly to the right of it. What can you say about Yeah. So can you find a neighborhood of the point that is also in this region? That is also in H plus?
Yes.
Yeah. So that's
Yeah, if we define it to be continuous, then it should be.
exactly, yeah. This is continuity. So it means that nearby points sort of map nearby. So if I have a H plus point, then like in a tiny region around it, like I can always find more H plus points. So this is continuity. And so this part might be a little hard to justify, but uh, I think I'll so to properly justify it, I would need tools from topology like compactness and a few other things. But I guess it's slightly intuitive, at least from what we discussed now. So every point has a tiny neighborhood that is of the same color. So intuitively, you can find a neighborhood tiny enough. So you can say that for every point, you can find a tiny enough neighborhood that contains points of the same type. And basically, what I want to get to is I have this square. We started off with the square over here. And what I'm claiming is that you can draw a bunch of like really tiny hexagons all throughout the square, such that uh, if I have a point lying somewhere over here, let me choose a color. Yeah. If I have a point somewhere over here, then uh, everything in that hexagon is of the same type. Like if this is an H plus point, then everything in that hexagon is the same kind. And this and yeah, again, like to properly justify this, I would need slightly sophisticated tools. But we've already sort of motivated the fact that every point has some neighborhood containing similar points. So hopefully it's not too big a leap. And such a thing is possible uh, only if there are no fixed points. Because otherwise there would be some point that lies in none of these sets, and you can't find this nice hexagonation of the entire square such that every point is contained in a hexagon that contains points of the same type. I hope that made sense. I'll describe the coloring of this, and hopefully it will make a little more sense. If it doesn't, then yeah, I can clarify things. So to summarize what we've done so far, we've taken a square. We have a map going from the square to itself, and we've defined these 4 regions of the square. And we are assuming that every point lies in one of these regions. In other words, we're assuming that there are no fixed points. So, and with this assumption, we've sort of argued that we can find tiny enough hexagons such that every point is contained within a hexagon, and every point in this hexagon is of the same type. And now we'll define a coloring of this thing, because after all, to say anything about hexagons, we need to color the board. So, right. All points in the hexagon are either in H plus or H minus, then we color it blue. If all points are either in V plus or V minus, we color it red. And we've seen that a point can be both in H plus and V plus, or a bunch of those combinations. So in that case, you pick a color at random. It doesn't really matter. Just pick some random color. And yeah, so we get a nice coloring of the board in this case. So yeah, now we'll sort of argue that we can't have a tile from H plus and H minus adjacent to each other. Can somebody guess why? It's got to do with continuity. So just to remind you, H plus is all those things that map slightly to the
Yes.
Yeah, go on.
No, sorry. No.
Oh no. Yeah, I wasn't going to say anything profound or anything. You can go on.
No, my argument was wrong.
I'm sorry, I couldn't hear you. No, go on. I don't have much to say.
I don't either.
All right, so yeah, maybe I'll say a few more stuff so that you can guess why this is true. So like we have these like really tiny hexagons, and we're saying that H plus, we're saying that one hexagon is colored, one hexagon is in H plus entirely. So that means every point of it maps slightly rightwards. And let's say we have another hexagon right next to it, where every point maps slightly leftwards. What can you say about the boundary? Boundary between these two hexagons. They're two adjacent hexagons, right? Let me try to draw things out. So let's say you have a hexagon over here.
Then the boundary points don't map either rightward or leftward.
Yeah,
They are fixed.
they map both rightward and leftward, which is a contradiction. So, or in other words, yeah. I think we said the same thing. Yeah. So if these things are mapping leftwards, these things are mapping rightwards, and f is continuous, somewhere over here they need to be fixed with respect to the horizontal direction. In other words, this must be in the this must be in some red region, either v plus or v minus, but not in certain. So we can't have these two things being adjacent. And this is like the crucial observation that will lead us to the proof. Right. Oh yeah, I already covered this. Right. So now that we have a hexagonal grid and we have this nice coloring, what can you say? Remember what we're assuming. We have a hexagonal grid, it's all colored, and we're trying to prove Brouwer's fixed point theorem. So which theorem should we apply here? I mean, like there are only two theorems over here, and it's not Brouwer's fixed point theorem. All right, I'll go ahead because we're sort of running out of time, but essentially now we have this, we've taken the square, we've filled it in with a bunch of hexagons such that every hexagon is either in h plus or h minus or v plus or v minus. And we've colored things red and blue such that we can't have any two adjacent things in h plus and h minus or v plus and v minus. And since by assumption there are no fixed points, so everything is colored, the entire square is colored, we can apply the Hex theorem, which says that you can find a path of red stretching from top to bottom, or you can find a path of blue stretching from left to right. So let's say we have a path of blue stretching from left to right without loss of generality. So let's say this is our board, bunch of hexagons. I really should have added another image over here. But what it's saying is we have a bunch of blue hexagons spanning from left to right on the square. All right, so since these are blue, these are either in h plus or h minus, right? What can you say about this thing, like at the extreme left? Is it in h plus or h minus?
This is an h minus. Minus is left, right?
Minus is, hold on, let's see what h plus and h minus stand for. H minus is to the left.
All right, it's h minus then.
Why do you say so? I'm talking about this point. I mean, you're sort of on the right track, but I think like you're confused between h plus and h minus. Or go ahead and tell your reason. I think like it's just a matter of sign.
I think I'm confused now.
I think it is H plus. H plus is right?
Yeah, h plus means the image is to the right.
Because there's no mapping to the left of the this one, it has to go to right.
Exactly, it's at the left corner. So I mean, there's nothing to the left of it. There's no way for it to be.
Yeah.
Yeah, there's no way it can map to the left of it. So it has to be an h plus. So I'll just write a plus over here. And what can you say about this thing? This shouldn't be too hard now.
That's h minus.
Minus.
Yeah, this is h minus because, you know, like, yeah, there's no way for it to map to the right. So it has to map to the left since we're assuming.
So now somehow there is some connection in a plus and minus.
Exactly. So here you have a bunch of pluses.
Yeah, so there must be a boundary in the middle where there must be a fixed point.
Exactly. There must be either a plus, and there must be a plus somewhere over here and a minus somewhere over here meeting. But then if you go back to our previous argument, you can't have a h plus and h minus meeting. So this is a contradiction. And since h plus and h minus cannot meet, this means that our
All
assumption
the
failed.
points are not plotted.
Exactly. All the points are not plotted. There is a fixed point that we didn't detect. So yeah, and the same argument applies in the top direction, like with the reds. Exactly the same argument. So that's basically it. Again, like this talk wasn't meant to go into the details of things. Hopefully, even if you've just got an intuitive flavor of the arguments, that should be enough. That was my objective. Uh, yeah, and there are more generalizations to this. Like we've seen a very cool connection between two unrelated areas of math. And so this led this person who initially discovered this conjecture, this connection, David Gale, to generalize the hexagram to n dimensions, and likewise prove the general Brouwer 6-point theorem in terms of hex. So that is very cool, and I hope you found this interesting. Here is the original paper of David Gale. Here are a few other references. And if you're interested in watching some videos related to this, uh, here's a proof of Brouwer's 6-point theorem in terms of this combinatorial result called Sperner's lemma. And here's a video by PBS Infinite Series about the proof of Brouwer's 6-point theorem. And so I'd also encourage you to have a look at the proof of, like, the combinatorial proof of the game of hex, and as well as the proof of Brouwer's 6-point theorem. These are both very nice results, and like they have very nice proofs. Unfortunately, I couldn't cover them in this talk because I thought 4 proofs would be too heavy, but they're fairly standard and easy to understand. And yeah, I'd encourage you to take a look at them if you find this stuff interesting. All right, are there any questions?
Yeah. How exactly does the generalization to n dimensions work?
Oh, so it's something like this. So let's say you have a cube full of like these 3D hexagons, and then you color them in one of 3 colors. Then the Hex theorem says that there's at least one path of one color connecting opposite edges, opposite faces of the cube. And that's the 3D version, and you can see how it generalizes to ND. N colors, N players, N pairs of opposite faces, and yeah, and so on. And there's a path always between opposite things. And Brouwer's 6-point theorem in 3D basically says that if you have a ball instead of a sphere, or like you have a coffee cup, you mix the entire cup instead of just the surface. Even then you'll end up with a fixed point. So that's what Brouwer's 6-point theorem says. Yeah, I hope that answers the question. Yeah, go ahead. You have your hand raised.
Yeah. So the Nash equilibrium, like the existence of the Nash equilibrium is proven using the Brouwer's fixed point theorem, right? So is there some, and we can prove the Brouwer's fixed point theorem based on the game of like the generalized game of hex. So is there some construction under which for all games where the Nash equilibrium exists, or wherever there's a strategy profile which is the Nash equilibrium, does that map to like a corresponding analog on the game of hex?
That's an interesting question, and unfortunately, I don't have a good answer. But I doubt this generalizes to arbitrary games because, like, we are using a few topological facts about the board itself, like the board of the game of hex. Like we are crucially using some topological facts here, and like we want a path between the two endpoints for, I mean, two opposite edges for example. And yeah, so I don't expect it to sort of generalize in this way, but I don't know a lot about these things, so I may be wrong as well. But yeah, that's just my.
Okay, thank you.
Hi Anand.
Hi.
If instead of a rhombus board, you have like a 3-player game with the hexagonal board. You understand what I'm trying to say? Hexagon
Yeah,
is
you're
one
talking about something like this, right?
Right. Right, correct. Would you still have something like the hex theorem, or does it fail in that game?
Interesting question. Like, and
Yeah.
2 players or 3 players?
Yeah, 3 players. Of course, 3 players. I mean, two
Right.
players maybe it will probably fail, but 3 players there might be a chance that it succeeds or something.
3 players, I doubt it. I think there'll be like too much chaos. Like, wait. So
Right,
let's try a counting argument. Like, so so if we have 3 players, then we expect roughly 1/3 of the pieces to be
right.
green color. And if we look at the diameter, I think the diameter.
Oh, right. No, no, it will fail. It will fail. So because you'll have moves where you have like one player puts a first color on one of the triangles, then another player puts another color on the adjacent one, and the third one puts it below or above. Yeah, right. That will fail. Fail. Yes. Okay.
Cool. Yeah, but this would be interesting. Like
Yeah.
this sort of a game. Yeah.
All right. See you.
Cool. Are there any other questions? Or should we wrap up? So I promised to show the strategy steering argument, but I think I changed my mind. Like maybe we can discuss this during the Mimamsa meeting because there's another thing happening now at 6 o'clock. But if there are any questions, I'd be happy to stay along and answer them.
Yeah, Anand, maybe I could like stop the recording now. So yeah. Thank you, Anand, for giving the talk. It was wonderful. Thank you.
Thank you. Yeah.